Hi, let's take a look now at circular motion, and we begin by looking at a few examples that illustrate exactly what we mean when we say circular motion. Here we have a vertical circular track and a skateboarder is about to go around it. He's currently outside the frame, but he's coming towards this track moving along a straight line, and he'll then hit the loop and exit. So let's take a look at it. Let's take a closer look at what we just witnessed. What we have here in this skateboarder is an object traveling with circular motion. As the skateboarder approaches the loop, let's assume that he does so traveling with a constant speed and in a straight line. On hitting the loop, the skateboarder's direction of travel continuously changes as he goes around this loop. Now, if you remember Newton's first law, the natural state of motion for any object is either rest or motion in a straight line with constant speed. The only way you can get something to change its direction of travel is if you have some force or forces compelling it to change direction. So that brings us to the big question here then. What is the force making the skateboarder change direction continuously as he goes around this loop? All along, as this skateboarder is moving along this track, there are three forces acting on him. There is the pull of the earth on him, which we call his weight. There is the push of the surface track against him, which we call the normal force, and there is also friction. Now, to make this analysis a lot simpler, we're going to ignore friction for right now. So as he comes along this track, the straight portion of it, none of these forces are compelling him to change direction. But when the skateboarder reaches this area, we begin to see that due to the shape of the track and its orientation in space, the track itself, the normal force that the track exerts on the skateboarder, is now compelling that skateboarder to go around in a circle. Of course, the pull of gravity is also having an effect on the skateboarder, and at certain points, that pull of gravity is also contributing to make him go around in a circle. So at this point, both the pull of gravity and the normal force pushing against him are both compelling him to go around in a circle. Before we move on, there are 2 points I want to stress. One, whenever an object moves in a circle, there must be some net force compelling it to do so. That net force we will call the centripetal force. Centripetal. In this case, the centripetal force then is made up of both the skateboarder's weight and the normal force that the surface is exerting on him. The second point is that the centripetal force always acts towards the center of the circle. So if we were to draw a vector here representing the centripetal force, which would be the vector sum of the weight and the normal force, then that force would be pointing towards the center of the circle. So let's restate that. Whenever an object moves in a circle, there must be some net force, which we will call the centripetal force, acting on that object, compelling it to go around in a circle. That force will always act towards the center of the circle. Here we have another example of circular motion. In this case, an athlete is going to spin a ball around in a circle, and he does so using a string that's attached to the ball. So let's take a look at it. Here we have a ball that is going around in a circle. The question is, what force is compelling it to do so? To answer that question, let's look at the forces acting on the ball. If we ignore air friction, then it's pretty easy to determine that there is the pull of gravity acting downward on this ball, and there is also the tension in this string. So now, the weight obviously is not making it go around in a circle. And we can tell that because the weight is not acting towards the center of the circle at all. The only force that is acting towards the center of the circle, at least somewhat, is the tension in this rope. So we could draw that. So here I've drawn a vector depicting the tension acting on this ball. So the string or the rope is pulling on this ball and forcing it to go around in a circle. Notice this force acts towards the center of the circle somewhat. As this ball moves around in a circle, the string is not exactly horizontal, and so this tension is not, as it is here, isn't acting directly towards the center of the circle. So the centripetal force is really a component of this force. The component of this force that does act towards the center of the circle, that is a centripetal force. So later on when we solve some problems, we look at this again in more detail. So let's look at some other examples. Here we have a typical ride found in many amusement parks. Let's look at the forces acting on one of these riders. If we take this rider for example, we see that there's tension here and there's another cable coming up here which we can't see. So we have two cables in this direction, and of course there's a tension in each of those cables. So we can just sum those two forces up as one force and we'll call it tension, represented with one vector. Of course there's also the weight. So let's draw some vectors depicting then the net tension and the weight. So here we have drawn the vectors. So this vector represents the weight of this person, and this vector represents the sum of the tensions in both these cables. So which force now is responsible for the centripetal force? Notice this thing is going around in a circle. He goes around in a circle more or less like that. It's kind of hard to show here. Anyway, the weight here again doesn't provide any centripetal force at all. It's the tension, but not the tension per se, or not the tension as it is right here. This tension has two components, a vertical component and a horizontal component. It's the horizontal component which acts towards the center of the circle and in fact provides the centripetal action. So what I've done here is I've taken this force and resolved it to show the two components. So this component, this is what is providing the centripetal force. So this component is the centripetal force. Notice there is no special force called the centripetal force. The centripetal force is just any force that can cause something to go around in a circle. So in this case, it's the tension, or this component of the tension, that is the centripetal force. In other situations, as we have seen, the centripetal force could be the normal reaction and even weight. Here, however, the weight doesn't contribute at all to the circular motion. These vectors are not drawn to scale. This component of the tension has to be equal to the weight. That's why this rider doesn't go up or down, at least not at this instant in time. Maybe I should have drawn this a bit bigger or something to show this component equal in magnitude to this one, to this weight. Anyway, we'll practice this later on. So this force, this component, is the centripetal force, and it's going to be equal to the mass times the acceleration of this person. Remember, he's going around in a circle, so his direction is constantly changing, so the velocity is changing, therefore he is accelerating. Newton's second law says the net force has to be equal to the mass times the acceleration, and so this is the net force acting towards the center of the circle, and that has to be equal to the product of this person's mass and his acceleration, which is also a vector pointing in the direction of the net force, which means it has to point in this direction also. So centripetal force causes centripetal acceleration. We will look at all of this again a little bit later on. Here we have a skier going around in a circle. Can you see the force that's providing the centripetal acceleration? So pause for a while and think about it. Okay, so right here where the ski board meets the water itself is exerting a force more or less in this direction. This force has two components, one parallel to the surface of the water and one that is perpendicular, obviously, and it's the parallel component that is forcing this skier to go around in a circle. When the skier is ready to continue traveling in a straight line, he'll simply reorient the ski board so that it's flat on the surface. In this case, this man is exerting a force, and this pull is what's responsible for making this little girl go around in a circle. So we can look at that force and see that this is actually the component. Remember, this girl goes around in a circle, so the center of the motion is somewhere about here as she goes around, and the centripetal force has to act towards that center. So this is the pull that the man is exerting. Note that this girl also pulls on this man, but we're not showing that force. So this force, of course, has two components. This force will be equal to her weight. So I haven't drawn that vector here. But this force, this is the unbalanced force, and this is the force that's causing her to move around in a circle. So as she goes around in a circle, she accelerates towards the center of the circle. Remember, we said the center of the circle is somewhere around here, as she goes around and around and around. In this case, we have two forces acting downward on this cart. There's the push, the normal force that this surface exerts on the cart, and of course the earth is pulling on the cart. So those two forces together combined to give us the centripetal force acting on this cart here. So we have seen something like this before when the person on the skateboard went around. The forces responsible for the centripetal acceleration were the same. Here we have a car moving along this little dip. Let's look at the forces acting on the car. There is the weight acting downward and the normal force pushing upward. And this then is the circular path along which the car is moving. And so the centripetal force is due to this normal reaction. Actually, the net force is this force minus this one. So the net force is the difference between these two. So let's make that very clear. So the net force is this vector minus this vector, and this net force is the centripetal force responsible for this acceleration. And here we have some other examples. We have seen one like this already. The tension in the string here is responsible for making this object go around in the circle. Actually, it's a component of this tension that is straight across here like this. So here, the force that allows this car to take the curve is friction. So if there were no friction here, if somebody threw oil on this road, this car would not be able to take the curve. So friction is the force that obliges this car to go around in a circle. Here, these roads are designed like this so that even in the absence of friction, let's say on a rainy day, this car should be able to safely take this curve if it's driving at the right speed. The forces acting on this car would be the weight, which I have not depicted, and the normal force. So this normal force is going to have two components. A vertical component which will be equal to the weight, and a horizontal component, and it is that horizontal component pointing towards the center of the circle. Notice as this car goes around, its trajectory is that of a circle, right, with the center here. So the horizontal component of this force is pushing this car around in that circle. So note, whenever something goes around in a circle, there is some force that is providing the centripetal acceleration. So there must be some centripetal force, in this case the normal reaction. Just like in the case where the person with the skateboard went around the loop and the normal reaction forced the skateboarder to go in a circle, that's the same thing that's happening here. The normal reaction, the road is pushing the car around in a circle. And here we have the earth moving around the sun. Obviously this is not drawn to scale. The earth would be like a minute little speck that you couldn't see if we drew the sun this large. Anyway, can anybody tell me what force is responsible for making the earth go around? Actually, the trajectory of the earth is elliptical, not circular, but we'll kind of stretch things a bit for right now and treat it like it's circular. So if you pause this for a while and think about it and see if you can figure out what that force is. Okay, so if you guessed that it's a pull of gravity, you would be correct. So this sun is pulling the earth with a gravitational force, and it's that gravitational pull that makes the sun go around in a circle. If the sun suddenly disappeared, the earth would simply travel off in a straight line from that point on. So in this case, the centripetal force is being provided by gravity. This is the same force that makes the moon go around the earth, and satellites that go around the earth, and the space shuttle, for example, when in orbit around the earth. All of these motions are due to the pull of gravity, and so we look at that in more detail as we move through this course. Here we have a bucket, and there's some water in here that you can't see, and it's attached to this rope. So the centripetal force that's making this bucket go around is obviously due to the tension in this rope. But what force is responsible for the centripetal acceleration of the water in the bucket? Think about it for a while. Pause and come back. Okay, if you guessed normal reaction, you would be correct. So the bottom of this pail is pushing the water around in a circle. So whenever there's circular motion, there is always some centripetal force, which could be a single force or the resultant of different forces, and that centripetal force will always act towards the center of the circle. So let's define circular motion and look at two very important properties of circular motion. Essentially, an object is traveling with circular motion if it's going around in a circle. Now, two very important properties of such motion. One, even if it's traveling at a constant speed. Since it's constantly changing direction, it is accelerating. Remember, velocity is both speed and direction. So if the direction is changing, the velocity is changing, therefore the object is accelerating. Obviously, if an object is accelerating, there must be some net force acting in the direction of that acceleration. And so that net force we're going to call centripetal force. Likewise, the acceleration is centripetal acceleration. So when an object moves around in a circle, the net force making it go around in a circle is called centripetal force, and it's making the object undergo centripetal acceleration. So that's it for this video.